And welcome to the physics video lecture once again. This is Physics 4B video lecture 19. We're starting something new, namely the chapter on magnetism. And I'll just begin with some general points linking everything that we've done so far. So let's put here next, this is a new chapter, magnetism. You know, the subject is always electricity and magnetism. They belong together. So far we've just done electricity. And let me briefly review just the way we've built up physics so far. So we start with mechanics. That's physics 4A. And you know, we have Newton's law. And we have kilograms, meters, and seconds, right? We have mass, we have space and time. Mass, space, and time. And everything we build up is reducible to these quantities, kilograms, meters, and seconds. Now this semester we started with thermal physics. And there we're talking about heat phenomena. But it turns out that thermal physics, via the ideas of atomism, thermal physics and statistical physics, reducible to these quantities here. We didn't have to introduce anything beyond, beyond kilograms, meters, and seconds. Then we did electricity, and we did introduce something new. We still had our concepts of force and energy and so forth, but we did have a new quantity. It was charge. In plus and minus, it was, I'll just write charge plus or minus Q, and the unit was the coulomb. So we did have something new. It's no longer kilograms, meters, and seconds exclusively, but kilograms, meters, seconds, and coulombs. That's something different. So next we have magnetism. These two subjects go together. We'll start with some phenomena, but we're actually going to find that we don't need anything beyond what we already have here in electricity, namely charge. So we'll start with some phenomena of magnetism. I have some bar magnets here and some other stuff that I'll briefly show you. So, magnetic phenomena. And what we'll have to suffice here is this bar magnet. Looks kind of like a bar magnet. Actually, it's a collection of little magnets I can pull apart. But the interesting thing is, say I break them in the middle here, I have 3 on each side. There's that attractive force that you guys have possibly experienced if you had magnets to work with. If I turn one of them around, there's now a repulsive force. Repulsive force I can feel, turn it around, attraction, okay? Now the interesting thing is, I can repeat this here, break this one off, there's the attraction, I can turn it around, and there's repulsion. It turns out I could take slices of this, like if I were to saw this one in half, the same thing would hold true. I would never isolate what's called a single pole, but rather this magnet has what's called a north pole and a south pole, and any of these magnets will be the same thing. We'll say that like poles repel and opposite poles attract. And the idea of the pole comes from the fact that if I were to suspend this from a string, it would orient itself towards north, magnetic north of Earth. Okay, so Earth itself has magnetic properties, the Earth, the planet as a whole. So I'll just say we have here bar magnets draw something here. So bar magnet, we've got a bar magnet north and south. That's just the convention, but it has to do with north and south on Earth. But right now we just have a bar magnet with north and south poles, and we find that like poles repel. And what does that mean? There's an interaction. I'm feeling a force. So there is a force interaction. So we already have a magnetic force. Like poles repel, unlike poles attract. So this is just what you learned with these bar magnets. And compass needles. Put a question mark there. Now I have another demonstration I have that I'm going to point the camera at in a moment. I have a very powerful magnet that I want to do a demonstration with. So let's see. We just tilt down. So that's a powerful magnet. Don't take my word for it. I have an array of compass needles here, and I'm assuming it's going to work. Let me consult the picture here. Yeah, this should work. So let's have a look at this array of needles here. Okay, you'll see the curvature in them, and I can't do both things at the same time. Okay, I'm going to have to check the camera once more. Are we seeing both? I think we're seeing enough. Okay, so we have this array of compass needles, and you see they're curved here. If I move them around, you can see them move. What you're seeing is the magnetic field. So these compass needles are little magnets that are lining up with the effect of this powerful magnet. Oh yes, I have an idea here. Just to convince you guys that this magnet is powerful, I'll just throw some metal at it. Okay, it takes quite a bit of strength to pull these out. So once again, we're going to look at these compass needles, and I'm going to, I got to consult the picture again. Yeah, this will work. Okay. So now just look at a single needle as I move. Focus on a single needle and see how many degrees it rotates. You should see a full 360 degrees. Okay. And also, as I hold this up here, you can see the shape that the needles conform to. They're conforming to what we call the magnetic field. Okay. Okay, so that was your demo. And right up here, if I go farther away, you can see how that moves. Okay, powerful magnet. Back to the board. Okay, good. I'll just go back to drawing my pictures. In here. So compass needles between, what I'm going to do is draw that powerful magnet I'm told it came off a ship out of the Second World War. Who knows? So the demo magnet, it's this giant thing here. Mounted to this, and when I hold the array of compass needles here, you actually start to see this type of pattern where the needles are lining up. Okay, you guys could take a screenshot, print it out, and add it to your notes. Okay, this is just as a reminder of what we saw here. Okay, so what I'm going to show you now is what you will see if you take a nice bar magnet, north and south pole, and either hold compass needles up to it or sprinkle iron filings. What happens is these objects line up with the magnetic field. So I can already talk about the magnetic field. And it is a vector. And I've tried to make it visible with those demonstrations there. It gets the name B. So B with a vector field, that's magnetic field. Field of a dipole. So a magnetic dipole, this is the phenomenon I was just showing you. So let's say there's a north pole and a south pole. How about another color? Well, so I'm just going to draw some of these field lines. I hope you recognize these shapes. This is what I just showed you. This is when we were following the compass needles around. In terms of the direction of the field leaves the north pole and enters the south pole. Okay. So that's the magnetic dipole field. And what we found, even with my demonstrations up here, is that we cannot isolate a north or a south pole. They always come together. No matter how thin I slice this thing, it's always just going to have north and south poles. In fact, you can buy pretty flat magnets that'll have that property. Okay. So we've got the magnetic field. This is the dipole field, so this one's very important. But the question would be, how do we create a uniform field? How to produce a uniform field? Question mark. Well, actually, that device I just showed you gives the answer. The north and south poles are, here, let's show you it again. Back to the board there. Yeah, the north and south poles are separated on the device I just showed you. So to create a uniform field, you just have to have, say, two magnets end to end. And I'll go ahead and give bar magnets and say I have north and south and north and south. And the idea is to bring these close enough together so that you get a uniform field in the gap between them. And that's exactly what that device does that I showed you there. You can get a very powerful field between those two poles, the north and south. So even though these things are, complicated and curved, if you put these north and south poles close enough together, you're going to have a uniform field. And a uniform field is to say a constant field, and we like constant fields. We can work with them. Okay, we can do a lot with a constant field, with a uniform field. So that's how to produce a uniform field. Okay, so that's the phenomenological part of what I was going to talk about. Let's see. Field lines. Very good. And by the way, when I showed that array of compass needles and I went like this around the around that magnet up front, I wanted you to see that the arrows are in this direction, and if you follow it around, it does a complete 360 degrees. Okay, so I think I showed that to you, and you can rewind the tape and have a look at it some more. Good, yeah, these are the phenomena I'll restrict ourselves to. And so far, there's no connection to electricity. So that's what we're going to do next. What's the connection of these phenomena to electricity? Okay, so next, connection to electricity. To electricity. And the basic phenomenon is that if you put a current carrying wire in a magnetic field, a force will act on it. You'll feel a force, but we're going to discuss that in terms of an electric charge. So they say a point particle charge in an electric charge in a magnetic field. So electric charge in a magnetic field. And there are just a great list of phenomena that go with this and applications. So we're thinking of a point charge in a magnetic field. And there's a whole bunch of properties now that I'm going to list. First of all, if you have an electric charge in a magnetic field and it's not moving, nothing happens, okay? So, no force if speed v equals 0. Okay. Actually, I should say, so I'm saying electric charge in a magnetic field, I'm thinking of a charged particle. Fundamentally, we're talking about electrons and protons, for starters, okay? So, there's no force if the speed is equal to 0. Now, if there is a speed or a velocity, there's a force, but it has a whole bunch of interesting properties. I'm just going to have to, you know what? What I'm going to do is write the force formula for a moving charge See, there's a whole list of phenomena that you could isolate, but what you find is that the force is proportional to the charge, and the cross product of the velocity and the magnetic field. So I'm assuming people have seen the cross product before. This is a mathematical object that's actually pretty rich. It takes two vectors and assigns a third vector to them. And maybe I'll review the cross product because it's so important. But yeah, interestingly, you know, in my notes here I have this list of 5 properties, and they summarize to the cross product. So a lot of experiments were done to extract this formula. Okay, so it's very rich, and let's just go ahead and look at them piece by piece. So what about this cross product? It has a bunch of properties. If you reverse the order of these two factors, you get a minus sign out of it. If V and V are parallel, the force is 0. Okay. The force is perpendicular to the plane that's spanned by these two vectors. Therefore, it's perpendicular to each of these vectors individually. Right? You can imagine experimentally how to discover that. It's quite interesting. And then you come up with this formula here. So we've got that cross product. I'll put an exclamation point and just give its formal properties, and then we'll see that they are the physical properties that are seen when you subject a moving particle to a magnetic field. So let's have a look here at the cross product. Hopefully you've seen it before, but a review never hurts. So the abstract properties, I'll just say for two vectors A and B, okay. So cross product, yeah, also referred to as the vector product, cross product. So it assigns, unlike the scalar product, it assigns a vector to two vectors. So let's suppose C is equal to A cross B. Then we have C is perpendicular to A and C is perpendicular to B. So if you think of these two vectors as spanning a plane, then the cross product is perpendicular to that plane. So C perpendicular to A and B, and A, let's just say A, B, C, right, C being the product, form a right-hand system. So they form a right-hand system. And B cross A is equal to minus A cross B. So if you reverse the order, you get a minus sign there. And the magnitude of C is equal to the product of the magnitudes of A and B times the sine of the angle between A and B. Now, let's give an example. When I said a right-hand system, how about we just look at our ordinary coordinate system like this? So, you know, this is the X, that's supposed to be the X, Y, and Z axes. And you know we can draw unit vectors along these axes. So we can have I hat, J hat, and K hat. So those unit vectors form a right-hand system. That's a good way to look at this. So the unit vectors I hat, J hat, K hat are a right-hand system with the following. I hat cross J hat equals K hat. So if you can visualize, I'm gonna write these formulas down, then we'll try to visualize it. So I hat cross J hat equals K hat, and then J hat cross K hat equals I hat, and K hat cross J hat, no, K hat cross I hat equals J hat. So this is just a cyclic process that I'm showing you. So let's start with this first one here. This is a good way to see the right hand rule and everything. Imagine I hat's pointing out of the board. I'm going to cross it physically. I'm going to turn it into J hat. So it's here, and I'm going to rotate it into J hat, and that gives me K hat. Okay. Well, that's just like turning a right hand thread. So if I'll use blue here. So if I turn I hat into J hat, I rotate I hat into J hat, you can hopefully recognize that that's a right hand thread, and that would extend up in the K hat direction if I twist something, right? So that's what it means for it to form a right hand system. And if you've used hand tools, then this should be clear to you. And then you can see my next one, J hat cross K hat. I'm turning J hat into K hat, and see I'm turning counterclockwise like that, and therefore it's coming out of the board at I hat. And the third one works the same. So our 3 unit vectors in this mutually perpendicular set of vectors in this coordinate system, in this right-hand coordinate system, can be expressed in terms of the vector product. Okay, so it's actually a very natural object for any type of rotational situation, which is where you may have run into it last semester. And it's just amazing that the force law turned out to be a vector product like that. Good. So for example, if you want to do a cross product, you can just use these rules if you have these unit vectors. Maybe I'll give an example of that. And then we'll just continue to discuss it in the context of the electrical phenomena, magnetic phenomena. Oh, and I mentioned it here, right? If the vectors are parallel, then the sign of the angle between them is 0, right? And there's a 0 magnitude. So parallel vectors have a vanishing, I'll just put this as a separate thing here. So if A and B are parallel, then A cross B is equal to 0. So in addition to these properties here, we also can say I hat cross I hat equals 0, J hat cross J hat equals 0, and the same for K hat. Okay, so a vector cross product with itself matches. Good. So one thing you can do is say A cross B equals AX I hat plus AY J hat plus AZ K hat cross product BX BY J hat plus BZ K hat. Now you do this cross product, you're going to get 3 times 3 is 9 products, but all the like I hat cross I hat ones are going to vanish. So you're actually going to get a big rule. You take this and these rules and you'll get a pretty complicated, but the actual rule for this here. So you're welcome to try that. It's a good exercise. It's also formally given by the determinant of this array here. This formal determinant, a good way to remember this, if you remember your determinant, is then your first component would be I hat, and then you do AY BZ minus AZ BY J hat, etc. Okay. So leave some room in your notes, and you can work that out as well for the formula. This will give you the same result that this big 3 times 3 product would give you. Okay. But so this is important. The understanding, this geometric understanding that when I rotate I hat into J hat, I rotate the x-axis into the y-axis. It's a right hand, like a screw, up into the z direction. Okay. And if I rotate the y into the x direction, then it's like backing out a screw, and therefore it's the negative direction. Good. So that's the kind of thing you have to study. And what we're going to do is talk a bit about the motion of charged particles now. And in fact, we'll go back to that force law. I'm going to consult the clock here. Very good. We'll go back to the force law and study it a bit. This was just a vector product review. And I'll do a couple examples. You guys can leave some room in your notes and do more. Let's see what the book has to say. So after that discussion, we're back to the force law. On a charged particle in a moving in a magnetic field, so force is equal to charge V cross B. You can also see, in addition to these vector product properties, if I had a negative charge, the force would be in the opposite direction as if I had a positive charge. Okay. So we've got that force law, but we've just introduced a new field, so we'd probably better talk about the units. Okay. So units of the B field, and then we'll continue on. Units of B. And how do we do that? Well, we're just going to look at this and solve it algebraically. So that would be the force over the charge times velocity. So first of all, we could say we have newtons, coulombs, meters per second. We could do that. We could also say it is kilograms, meters per second squared, and we still have coulombs and meters per second. And in that case, we would cancel these meters, one of these seconds, kilograms, seconds times coulombs would be one way to look at it. So yeah, these are always consistent SI units that we'll always be using, especially when we do our quizzes, right? If I say a B field of 1, then it's one of these. This is referred to as the Tesla. Okay, so the unit of the magnetic field is a Tesla, but its combination of other SI units are here. And in fact, there are other things we can do. Yeah, but we'll leave it at this, okay? We'll leave it at this. SI units. Other units may come up in time, but we'll just stick with this for now, that we have the Tesla. Okay, now let's go ahead and look at some examples. So, examples of the motion. So suppose we have, since we started with this, we've got our south pole here, we've got a north pole there, so we know that V is pointing in that direction. And suppose we send a particle into the board. Okay. So we send a particle into the board, so we're crossing a vector into the board in that direction there. So particle, I have to do red here. Particle into the board, and the idea is you draw an X for something going into the board, and you draw, well, I'll get there. You draw a dot for something coming out of the board. Good, X into the board. So we do that right-hand rule. We turn this way, okay, and the result is up. So I send something into the board with that cross B field, and there's a force that's going to point up, which means it's actually going to curve. Right? It's going to send the board, the force up, it's going to curve. So there are many examples of that type. Oh, by the way, that was a positive particle. A negative particle would curve down. Okay, so the book has a lot of those examples as well. And in fact, I'm continuing, unlike the book, I'm going to continue with the discussion of the motion of charged particles in a field. And then we'll get to the current carrying wires and stuff. I think the charged particles are more fundamental and pretty interesting. Okay, so let's do a couple more of those examples with the vector product. So this time we're going to take a magnetic field instead of this one here that goes from right to left. We're going to take one that is into the board. Okay, so B into the board, and the way we designate that is we draw a bunch of X's, with or without the circles around them. Okay. So this is to indicate that there's a B field that's pointing into the board. Now, what if it were pointing out of the board? If it were pointing out of the board, we would do circles with dots, or just dots. This equals out of the board. Let me write that a little clearly. And the way you can remember this really easily, this is an arrow coming at you, and this is the arrow going away from you, the feathers on the end of the arrow, and this is the point of the arrow coming at you, right? You can never forget it. So this is into the board, and what we're going to do is say that this is the region of the B field, and we're going to launch a particle. So plus Q, we're going to launch it into that field region. What happens when it enters the field? There's our law. Q is positive, V cross B. Okay. Now, V is up, and B is into the board. So I'll do this with my two vectors. V and B, okay, B is the red one, B is the blue one, and facing the board this way, I turn one into the other, right? I turn V into B, and in terms of the camera right now, towards the camera, in terms of the board here, to the left. So as soon as that particle enters here, it's going to veer off to the left. It's going to veer off to the left, and say it gets here. Well, it's going to keep veering off to the left. In fact, my next proof is going to be that if I launch a particle in the middle of a big field like this, it's going to do circular motion, which is where this gets really interesting. So that was my example. The next example, we're going to launch a particle, same scenario. Okay, so there's our region of B field. But we launch it right here. Okay. If we launch it at this point with V, it's going to veer around like this. Now, how do I know it's going to be a circle? From this definition here, the force is perpendicular to V. So it neither gains nor loses energy if there's no friction, if there are no collisions. Okay, so if it's in a vacuum. So since the force is always perpendicular to V, that's the definition of uniform circular motion. The force is perpendicular to V. So at this point, there's your velocity. The force is always towards the center. Let's do some red arrows here. Force gets over here, right? Force, and what are you looking at? You're looking at centripetal motion. So I want to give that a little bit more of a proof. I just stated it in words. Yeah. Let's make a little room here and then we'll get that proved. So I'm going to rewrite the force law, but so we're doing what? Motion of charged particle in a uniform magnetic field. So motion of charged particle in the uniform B field. That's what we call a magnetic field, B field. And the configuration, configuration has to be the way I said, the velocity is perpendicular to the B field. Okay, the B field's into the board, B field as above. Okay. So here are 2 points. First of all, the B field does no work on the particle. It doesn't do any work on it, so it doesn't change its kinetic energy. B field does no work on the particle, comma, because we've got F is Q V cross B. So so D work would be F dot dx, okay? Equals F dot dx dt times dt, okay? Now this is F dotted into V equals F dotted into V times dt, and if you do a dot product with this V here, because V and F are perpendicular, then you're going to have a dot product equaling 0, so dW is equal to 0. Okay, because that's equal to 0 right there. So because no work is done, the kinetic energy is unchanged, and therefore speed V is constant. Now the speed V is constant, but of course the velocity is changing because the direction's changing. But if the speed V is constant and the force is perpendicular to the velocity, that is uniform circular motion. Okay. Therefore we have uniform circular motion We have great demonstrations of this, by the way. I have to see if I can bring them in here. Maybe a little hard with the camera. Yeah, we'll see. Okay, so we've got the uniform circular motion. That's worth 2 exclamation points because we can set the formulas up very quickly now for the radius of the motion, the speed, and everything. Okay. Good. So let's go ahead and make this point next. So since we have uniform circular motion, we have M A centripetal is equal to F, right? Or mv squared over r is equal to F. Hope you guys remember this. This is from mechanics, mass times centripetal acceleration, which is v squared over r. Well, what is our force? We have it written down here. Here we go. Now, with this scenario here, V cross B, we have 90-degree angles in here, in my scenario, V and B. Therefore, the sine of 90 is 1. It's just Q times V times B. So the magnitude is Q times V times B. So you don't even have to memorize this formula. This you can always set up and attain and relate these quantities in the uniform circular motion to each other. Okay, you'll notice we can cancel one of the V's, and we're going to do that. I'm going to rewrite this solution that relates all of these quantities. Good. Or first we'll just cancel this. M over R is equal to Q times B. But there's an important point about all of this. Let's just solve for R. R is equal to M over R over Q over M. Now let's just leave this like this. What I do want to show is that 1 over R is equal to Q over M times B. Important point in all of this, once you have one of these formulas, you have it. So you don't have, if you remember this, you can always get this. What's important here is that this charge divided by mass always shows up, as a ratio. So these electromagnetic formulas that we now have don't allow us to discover the charge or the mass independently. So there was a bit of doing in the historical development to actually find Q and M individually, because Q over M is what always comes out. So note. So you'd be able to do an experiment, you'd be sending something in a circle, and actually I lost the V here, sorry. I lost the V, but I found it again. So MV over R, QV, so V over R. So yeah, the important note, Q over M, this ratio always appears. Q and M cannot be determined individually just using these formulas. Using F, and I'm going to call this F electromagnetic, because we already knew that the force was Q times E, right? But if you have electric fields and magnetic fields, it's Q V cross B added to there. So you can't determine Q and M individually because of the way these show up. Yeah, Newton's law, because M d squared R dt squared is equal to QE plus QV cross B. Oops, cross B. Okay. So every time you do a dynamics experiment, you divide both sides by M. What do you have? You have Q over M. right? You can't isolate them. So it took a little bit of doing to find Q individually, but once you find one of these two individually, Q or M, then an experiment along these lines will get you, the other one. Because this experiment will get you Q divided by M. Let me consult the clock here. Okay. So what I'm going to do is discuss some homework problems that are all going to work along these lines. So for starters, let's just leave this right here. You can use this in any of the number of these forms. Okay, so I wrote down some problems. I'll go ahead and put them up here and say a couple of words about them. I'll even write down where this comes from once again. So we have the circular motion. And Newton's law, mass times acceleration is equal to force. Mass times centripetal acceleration equal to force. So m v squared over r is equal to q v d. That's where it comes from for the circular motion. Now let's look at these problems together. I'm looking at chapter 26. Chapter 26, problems 19, 27, 28, 30, and 32. First we'll consult the book and then we'll see if we need all those. Okay, chapter 26. Yeah, the circular motion is such a great and important phenomenon here. Actually, let me just start here. So, 19, this one here, we're just using F equals Q V cross B. They tell us it's an electron, and they give us these vectors, we just have to calculate them out, okay, using the cross product. So that's a good basic exercise. But these other ones are the circular motion. So for problem 27, proton 65 centimeter radius. Well, of course, you got to convert to meters. Giving you a certain number of Teslas for the B field. And you want the orbital period and the speed. And the kinetic energy. So this was problem 19. So for problem 27, aside from converting to meters, what do we want here? The orbital period, the speed, the kinetic energy. Well, here's our, we can just do with this formula or this one, doesn't matter. They give us a radius, they tell us it's a proton, we know the mass, they give us a field, so we can calculate the speed. Yes, it's a proton. So yeah, there's just one unknown. We can calculate the speed, and from the speed, of course, we can calculate the kinetic energy. Okay. So V equals something, and then kinetic energy half mv squared, but they told us the proton, so you look up the mass of the proton, and so forth. Now what about the period? Orbital period. Well, remember, V times T is equal to 2 pi R. Because that's the speed times the time is the distance, and it's the distance around a circle. So this formula gets you the period. Okay, solve for the period, you already found V. Okay. 28 is similar. 28, they tell you the energy in kilo electron volts. You have to convert, so if you're given the kinetic energy, you have to convert to joules. One way to do it, okay. And you know it's an electron, so you can look up those masses, and that allows you to get the speed, and once you have the speed, you're right back to this formula over this one, okay. They give you the B field as well. So 28 is similar, and 30 and 32, what do we have there? $30 is an interesting one. I'm going to let you guys tangle with that. It's also circular motion, and they're giving you a bunch of different quantities. No numbers, beautiful. And you have to remember your definitions of linear momentum and stuff. And did I give 32 or 33? 32. Yeah, this one is really great. So 32. So 32 refers to a picture in the book, and I'll just draw a small version. There's a region with a B field, the way I discussed it before, and they're saying a charged particle is going to enter, it's going to enter with let's make a straight line here. It's going to enter with a certain angle, okay? Now, what does it do as soon as it enters? As soon as it enters, it is part of a curve of an arc-shaped trajectory, so arc-shaped like this, and based on the geometry, it's going to leave at a certain angle, and there's going to be a separation distance. So that could be a little challenging. I haven't done that one yet, but the fact is, it's just a section of circle. Okay, it's a section of circle as soon as it enters. So as soon as it enters, the data will tell you what the radius of that circle is, and that that center of that circle's out there because it's doing that arc shape. Good. So that could be interesting as well. Just an application, but very important application. And remember, you don't have to memorize any of these things. This is what's happening here. You go from here to here, and then you're on your way. Okay, good. We're going to leave it at that. See you guys next time.